Is the study of the universe as a whole, what it contains, how it began, and how it'll end. 100 years ago, scientists had no information about any of these things. We've learned a lot since then, especially in the last 30 years. In this lecture, I'll summarize our present day understanding of cosmology. Part 1 will cover the origin of the universe with the event we call the Big Bang. The figure on this slide shows some of the major events in the history of the universe. It all starts with the Big Bang at the left. The term Big Bang is misleading since the universe didn't explode into existence. In fact, it was coined by an opponent of this theory. Basically, he said, "You don't think the universe began with a Big Bang, do you?" Actually, no, we don't. But we do think it inflated incredibly rapidly for a very brief instant. This period of inflation lasted a billionth of a billionth of a billionth of a billionth of a second. So that's the rapid expansion that's shown on the left side after where it says quantum fluctuations. After that, after inflation, the universe continued to expand, but much more slowly. Actually, if you look to the right of the figure, you might notice something interesting happening with the expansion now. I won't get into that now. You'll have to wait until the end of the lecture. Now remember, when we look far away in space, we're also looking back in time. So we can look back billions of years by looking really far away with our powerful telescopes. Unfortunately, we can't look all the way back to the Big Bang 13.7 billion years ago, but we can see the light left over from the Big Bang, the afterglow, which was released 375,000 years after the Big Bang. After that, galaxies were born, and inside them, stars and planets. This figure shows how the background temperature of the universe has changed over time. I bet it's the craziest graph you've ever seen. It doesn't seem that crazy at first glance. It's just a line sloping down. But look at the axes. The x-axis shows number of seconds since the Big Bang. It starts at 10 to the negative 43 seconds. That's the furthest back we can go according to something called the uncertainty principle. So we can't go back to time equals 0, but we have theories that take us very, very close. The first second of the universe extends all the way to the right side of the figure. You see 10 to the minus 3, and then there's one tick, and then you see 10 to the 7. 10 to the 0 is 1. So 1 second into the universe would be roughly where the yellow and the green bands meet. So clearly a lot of things happen during the very first instant of the universe, and then a few more things happen during the first second, and then one more important thing happened in the first couple of minutes. The y-axis shows temperature. You can see that it was unimaginably hot at the very beginning, over 10 to the 32 Kelvin. But it cooled rapidly to trillions and then billions and then millions of Kelvin. Today, the background temperature of the universe is just a couple of Kelvin or a couple of degrees above absolute 0. You might be surprised and possibly disappointed to hear that at the very beginning there was no light or sound or even any matter. There was no stuff in the universe yet. There were just forces. Today there are 4 fundamental forces. The only one we've covered in detail in this course is gravity. We've also touched on electromagnetism here and there. But then there are 2 other forces called the strong force and the weak force, sometimes called the strong nuclear force and the weak nuclear force because they operate on the tiny scales of nuclei. We think that in the very beginning, these 4 forces were combined together. The last 2 to decouple were the electromagnetic force and the weak force. In fact, we can recombine them in the lab to create the electroweak force. We think the electroweak force decoupled from the strong force slightly earlier. All of this happened in the very first second of the universe, a tiny fraction of a second. We haven't yet been able to recreate the conditions in the laboratory to combine the electroweak force with the strong force, but at least we have a theoretical understanding of it. Those theories are called the grand unified theories. What we don't understand, even theoretically, is how to combine gravity with the other forces. If you figure that out, you'll definitely win the Nobel Prize and maybe even get an element named after you, or maybe the first colony on Mars named after you. Where did all the stuff in the universe, the matter and the light, come from? The rapid ballooning event called inflation, which took place during that first instant, could have created them. According to quantum physics, even empty space isn't completely empty. There are always tiny fluctuations, sometimes called quantum ripples. But these are billions of times smaller than even the smallest known fundamental particles, such as electrons and neutrinos. But inflation stretched everything out in the very beginning, so it could have magnified these quantum fluctuations to form the first particles. Inflation also solves what is known as the flatness problem. We live in a flat universe. Flat here doesn't mean two-dimensional. Galaxies do fill the full three-dimensional space that we can see. What we mean when we say the universe is flat is that space doesn't appear to be curved. If space were curved like a sphere, shown on the left, or like a saddle, shown on the right, light rays will bend as they travel from point A to point B. But it looks like they don't bend. Light rays travel in straight lines through space, except near very strong gravitational fields like that of a black hole. The thing is, when people like Einstein came up with equations describing the nature of space, a flat universe turned out to be an extraordinarily special case. There's no known physical reason for space to not be curved. Theoretically, it seems much more likely that the universe will have at least some curvature, either positive or negative. That's what's known as the flatness problem. Why is the universe curved when there's no known law of physics that says it should be? Here's how inflation solves this problem. Imagine an ant on a balloon. If the balloon is small enough, the ant can see that the balloon is curved. But if the balloon is greatly inflated, its surface looks flat to the ant. The balloon is still curved, but the ant can't see the curvature. We're the ants. The universe might actually have some curvature, but as far as our eyes can see. And by our eyes, I mean our most powerful telescopes. There is no detectable curvature. If this is right, that means the actual universe is likely to be way, 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 way larger than the observable universe. We can see billions of light years in every direction, and within that extent, the universe appears flat. Maybe the actual universe is so much larger, and there is curvature out there that we just can't detect because we're looking at such a tiny part of the universe. All right, that was some heavy stuff. Inflation is an extremely challenging concept. In fact, it wasn't even part of the original Big Bang Theory. It was added later to explain where the first particles come from. Also, to explain why space appears flat, and to explain some other things that I don't want to get into. But after inflation ended and the four forces became distinct, the universe should have been full of particles. Most fundamental particles, like electrons and neutrinos, and protons and neutrons, have a corresponding antiparticle. When a particle and its antiparticle come in contact with one another, they destroy each other and produce light, photons. theoretically we would expect an equal number of particles and antiparticles to have been produced. But if that had actually happened, we wouldn't exist because all of the particles and antiparticles would have been destroyed and there would be no matter left. So there must have been just a little bit more matter made than antimatter at the very beginning. We'd think there was one extra matter particle made for every billion matter-antimatter pairs. So for every billion antiprotons that were made, there were a billion plus one protons made. And likewise for electrons and neutrons and neutrinos, etc. Then an event took place which I like to call the First Great War. You probably never learned of this war before, which makes sense because there were no human lives lost and no human suffering. But imagine a war where a billion soldiers go in from one side, a billion going from the other side, and one walks out alive. And then this happens again, and again, and again. That's a bad war. That was a war that took place between matter and antimatter 1 millisecond after the Big Bang. And each time a matter particle and an antimatter particle collided, they destroyed each other and light was produced. So the universe had hardly any matter left and no antimatter left, and it had lots of light. It was mostly light. Okay? But some excess matter had been made, and so some matter survived. So you could say matter won the war, go matter. And we're made of that matter. This is the furthest back you can trace your ancestry. You might have traced your ancestry back to different communities in different countries, but why stop there? You can go back to the first Homo sapiens in Africa a couple 100,000 years ago, or the first hominids also in Africa a couple million years ago, or the first mammals 50 million years ago, the first life forms, the first cells 4 billion years ago. You can go back to the atoms made in the cores of dying stars before the solar system itself was born 4.5 billion years ago. Or you can go all the way back to the first millisecond of the universe 13.7 billion years ago to the matter that survived the Great War with antimatter. Then, over the first couple of minutes, nearly all of the universe's helium was made. The sun takes 10 billion years to turn most of the hydrogen in its core to helium. Why does it take so long? Because the sun has to do this with just protons being smashed together in the proton-proton chain. It would be a lot easier to make helium if there were free neutrons available. The thing about neutrons is they're unstable. They decay into other particles in around 13 minutes on average. So free neutrons won't stick around that long. But the universe wasn't 13 minutes old yet, so there were still neutrons available. So protons and neutrons stuck together to make deuterium, which is just H2, hydrogen with a proton and a neutron. From there are two different paths to produce helium-4. The most common type of helium. So you can have a deuterium stick to another deuterium, that's shown at the bottom here, to directly make a helium-4, or what's shown at the top right as a deuterium sticking to a proton. Once those stick together, it's just two protons and a neutron, which we call a helium-3. And then below that, you see one of those helium-3 nuclei colliding with a proton. Apparently, this turns one of those protons into a neutron, and you end up with helium-4 that way as well. Don't worry about any of these nuclear reactions. So these are details that you don't need to worry about. All I want you to know is that a couple minutes into the universe, the first couple minutes of the universe, helium was made, and when this was done, 90% of the ordinary matter was hydrogen, and the other 10% was helium. Heavier elements, everything heavier than helium pretty much, didn't exist yet because they're only made in stars, dying stars, supernovae especially, and no stars had formed yet. So the universe at this point is made of hydrogen nuclei which are just protons mostly, helium nuclei, typically two protons, two neutrons, and there are electrons too. Electrons aren't doing anything here, but they're also there. For every proton, you're going to have an electron to balance it out electrically, because for every positive charge, you need to have a negative charge, keeping things balanced. And then, for hundreds of thousands of years, nothing new happened. The universe kept expanding, and as it expanded, it cooled. The photons, which the universe is mostly made of, and these photons were made when the matter and antimatter destroyed each other. Those photons are bouncing off the hydrogen and helium nuclei and the free electrons. Light tends to scatter off charged particles. So the light is not free. It's constantly bouncing off the particles. So back then, the universe was a bright, dense fog. You couldn't see that far because the light's scattering around. So this light would be hitting you from every direction. And then, when the universe was 375,000 years old, it had cooled enough for the electrons to combine with the nuclei to make neutral atoms. So I drew these diagrams over here. On the left, you see the photons bouncing off electrons, protons, which are the H1s, the hydrogen nuclei, and the helium nuclei, two protons and two neutrons. Constantly, the light is bouncing off these particles. And then, 375,000 years in to the universe, electrons, so on the right, the electrons are orbiting the protons. They're also orbiting helium nuclei. So the electrons are now bound to the nuclei. That's what we call a neutral atom. And light doesn't scatter off neutral atoms the way it scatters off charged particles, and so the light is set free. The universe becomes transparent. And this light has been getting stretched out as the universe has been expanding. When it decoupled from matter 375,000 years after the Big Bang, it was actually visible light. The expansion of the universe has been stretching the light waves. The wavelengths have been getting longer. They've gone from the optical part of the spectrum to the infrared, and now to the microwave. And this light, or microwaves, were detected by these two men, Arno Penzias and Robert Wilson. They were working at Bell Labs in New Jersey, and around 1962 they started detecting some microwaves with this horn-shaped antenna, which they couldn't explain. There were no microwave ovens nearby. It wasn't coming from a radio station because it wasn't coming from New York City or any other nearby city. It wasn't coming from the sun because they could see it in the daytime and at night. Once they cleared out the pigeons living inside the horn-shaped antenna and the pigeon poop, they knew it wasn't coming from any of that either. And they knew it wasn't coming from the electronics. They tested everything out, and they just couldn't identify the source of these microwaves. Now, most people would have said, oh, well, big deal. It's not a strong signal. It's not bothering me. Let's move on. But these two were very persistent. They refused to give up. They kept telling people about it and asking them what it could be. One of them was a physicist nearby Princeton University, also in New Jersey, named Robert Dicke, who had been looking for the light left over from the Big Bang. Now, the Big Bang was not a household term at this point. These guys were physicists, engineers. They had heard about the Big Bang, but the man on the left, Bob Wilson, actually didn't even believe in the Big Bang. Like Fred Hoyle, who came up with the term Big Bang, he actually thought that the universe had always existed. But this was definitive evidence for the Big Bang. This is the clearest evidence that we've obtained supporting the Big Bang theory. And for that, Penzias and Wilson were awarded the Nobel Prize in 1978. Now I'm going to show you what this light left over from the Big Bang looks like. Here it is. It probably doesn't mean anything to you just yet. Hopefully, it will in a minute. The main thing to notice here is that it's not perfectly smooth and featureless. It's not all the same color. The colors are made up here. Well, they're all microwaves. But what we're seeing are places that are slightly more redshifted than the others. All of the light has been redshifted over the last 13.7 billion years as the universe has expanded, but some regions are more redshifted than others. Those are the ones that are shown in red. So what happened was when the light first decoupled from matter, again 375,000 years into the universe after the Big Bang, the matter pulled back on it gravitationally. When matter pulls on light, the light doesn't slow down. Light always travels at the same speed, but light does lose energy. This happens near black holes as well. Light loses energy by having its waves get longer. Its wavelength gets longer. So the red regions are the places where there was more matter in the universe when the light escaped from the matter 375,000 years after the Big Bang. So these were the seeds of the first galaxies. These are the denser regions of space where there was more matter, and these would go on to form the first galaxies. So this is the oldest picture we can get of the universe. This is a baby picture of the universe. It is the cosmic microwave background more than anything else that shows us that space is not curved. The only models of the universe that match up with the observed cosmic microwave background are the ones assuming a flat universe. So if you look at the square on the bottom left above the closed universe, you can see that the red and blue regions are a little too big compared to what we observe, which is shown above. And if it's a saddle-shaped or open universe, the one shown on the right, those red and blue regions look a little too small. The only fluctuations that match up with the observed one by an observatory called Boomerang is the one for a flat universe. Here's a summary of the key events in the early universe. Physics tells us we can't get any information going all the way back to time equals 0, but we can get very, very close. During the very first brief instant, lots of things happened, including the separation of forces and an extremely rapid expansion, which we call inflation. Then particles and antiparticles formed and destroyed each other, producing light. The tiny amount of matter which survived formed hydrogen 1, which is just a proton, and helium 4, which is 2 protons and 2 neutrons. That happened in the first couple of minutes. Then, 375,000 years later, electrons combined with the hydrogen and helium nuclei to make neutral atoms, and that set the light free. We can still see that light, which has been redshifted to the microwave part of the spectrum, in every direction of the sky. It's in this room, it's everywhere in the universe. It shows us the dense clouds that went on to form the first galaxies. This concludes part 1 of my lecture on cosmology. I'm done talking about the Big Bang. In part 2, I'll tell you what the universe is really made of and what lies in store for the future.